conjugate base. Okay. And every base has a conjugate acid. They differ by how many protons? One proton, right? Because you've donated a proton or you've accepted a proton. I should say base there, shouldn't I? Instead of just conjugate. Okay. If you look at our data booklet on the acid base, all the acids are on this side of the table, increasing in strength as we go up. All the bases are on the left side of the table, weak up here, strong as you go down. So if you are a weak acid, phenol, you are a somewhat strong base, right? They go hand in hand. That kind of makes sense. Okay, strong bases are at the bottom. The stronger the acid, the weaker the base, the conjugate base, I guess I'd say. All right. There are strong bases, so we have O2 minus. That is never going to exist by itself. Okay, at the very bottom, it's going to rip a proton off of water and produce two OH minuses. O2 minus, anything with a -2 charge isn't really that happy. It's not stable. So if there's any sort of proton around, it's just going to grab it. Okay. NH2 minus is going to rip a proton off. We're going to create ammonia and OH minus. They're 100%. They are not in equilibrium. They are the equivalent of the strong acids or the anti-strong acid. That's not a real chemical thing. The opposite of strong acids. Okay. Okay, there's no KBs in the table, right? But that doesn't mean we can calculate. We can't calculate one, okay? KB stands for the base equilibrium constant, essentially. So if we have the reaction of some base, doesn't matter, what's called X, we react it with water. We're going to get HX and OH minus. Come on. This is the K. So we can write a KB expression, just like we can write a Ka, a KSP, a KQ. They're all the same thing. It's the concentration of the products over the concentration of the reactants, excluding the pure water. So we get that. If we take the HX and write its Ka expression in water, and then go, okay, well, that's an acid reaction. So the Ka is equal to X minus. Okay. Those look, it's HX in the bottom. Sorry, thank you. There we go. They look fairly similar. They got a lot of the same stuff in there. Okay, so what we're going to do is multiply them together and see what happens. We're going to multiply the Ka and the Kb together. So we go, okay, Ka times the Kb and then we're all proficient in math, right? Sometimes. What's going to happen? Stuff's going to cancel. So HX cancels HX, X minus cancels X minus. We're left with where have you seen that before?
For water.
That's for water, and it equals the kW. So if you multiply the Ka and the Kb together, you get the Kw. What's the Kw? At 25 degrees. 25 or 20 degrees, whatever the temperature is. Okay? So, Ka, you need to remember this, times Kb equals Kw. All right. Therefore, we can calculate Kb's off of the Kw, which is a constant at a certain temperature, and the Ka, which we can always look up in our table. Go. Is it 1.0? Yeah, it is, and that's what I wrote. I don't know why I wrote 1.0.
I said that. No, you didn't want that.
All right. Okay. Now it's just a math problem. So determine the Kb for F minus at room temperature. Okay. So F minus, we throw it in some water. You're not actually throwing F minus into water. It'd be like sodium fluoride that you throw into water, but sodium's a spectator ion, so we just ignore it. So if I throw that into water, what happens? It receives a proton. I get HF plus OH minus. So it's acting as a base. Okay, so we can calculate the Kb. What's the formula for Kb? If I want to solve for Kb, yeah, if I divide the Ka off, I get Kb is equal to Kw over Ka. Kw we know, 1.0 as corrected, divided by 10 to the minus 14. Ka of what? Of HF, the conjugate acid. All right, it's the Ka of the conjugate acid. Okay. Ka of HF is, what is HF? Thank you. So the Kb is 2.9 times 10 to the minus 11. Is that a big number or a small number? Small number. So what is favored? Reactants, right? This is a tiny number. So not a lot of this happens. The equilibrium's over here mostly. Okay? All right. We have 10 minutes left. Oh, that works out okay. We'll do this one. I'll give you a couple. I mean, that would be a natural break anyway. All right. Kb for this. So we throw H2PO4 minus into water. Everything's in water. Everything that we do is in water. What happens? Sorry? What loses a proton? So the H2PO4 loses a proton. What are they asking for? Kb. What does that mean? It's a base. So is it losing or is it accepting a proton? It's accepting a proton. Because remember, water can act as an acid or a base too, right? So the H3PO4, and I get this. Hang on, it'll make sense in a sec. I hope. Okay. So we go, okay, Kb for this reaction is Kw over Ka. The Ka of phosphoric acid is fairly strong. 7.5 times 10 to the minus 3. So 1.3 times 10 to the minus 12, which means we're way to the left, right? It's a tiny number. Does that make sense? Yes, because which is going to be the stronger acid? Is this going to act like this acting as an acid? Okay, that could happen. But if this donates this and we form phosphoric, which is fairly strong, it's going to really push the thing this way. That's why we get a tiny equilibrium. Okay. If it asks for the Kb, you got to write the base equation. Okay. If it asks for the Ka, you can write the Ka equation. Okay. Does that make sense? So Ka times Kb equals the Kw, which is 1.0 times 10 to the minus 14. This is a natural break, actually, so it actually worked out okay. All I want you to do is numbers 1 to 3. Tomorrow we're doing a lab, so Friday we'll pick this up again. There's a couple of longer ice table ones to do. The next 2 days are going to be labs, people. So bring your lab hat.